Hi everybody, welcome back to another calculus video lesson. I wanted just to take a moment to talk about where we've been and also where we're headed. So by now, midway through the semester, the first semester in calculus, we've covered a lot of different rules on how to write and find derivatives. And that's one of the big components of this entire course: limits, derivatives, and then finally integrals. And this next unit that we're going to talk about deals with integration, integrals. And there's two kinds of integrals in calculus. They're called indefinite integrals and also definite integrals. And as you can see right here, I've got the notation on display for you in this video. The integral symbol is this elongated letter S, and it actually means sum, S-U-M. And in the two kinds of integrals that we have, I mentioned indefinites. Indefinite integrals just means that we're going to look for an antiderivative. We're going to find the antiderivative, a function, and then add a plus c, a constant of integration on it. But definite integrals are a little bit different. Definite integrals are going to be values. They represent the amount or net accumulation of area underneath a function curve. And so when we talk about an indefinite integral, we're talking about a function. When we talk about a definite integral, we're looking for a number, for a value. And definites you can always tell by the lower and upper bounds or the lower and upper limits of integration. So when you see tiny numbers at the bottom and top of your integral symbol, you're looking at a definite integral. And that is something that can be evaluated to a number, to a value, a numeric final answer. So how do we find the exact value of a definite integral? That's going to be a future video. But right now, what we're going to do in this lesson is talk about how to approximate values of definite integrals. And maybe the most famous way to do that is by using what is called a Riemann sum. And so what I'd like to do today is to talk about how we can approximate the value of a definite integral using a Riemann sum. And so just as a little bit of background right here, remember that the integral from a to b of f of x is essentially the definition of what a definite integral is. And it means the area under the function curve of f from the lower bound a up to the upper bound of b. Sometimes we say lower limit, upper limit, but it's the same idea for those. And this a value and the b value right here, those would be the lower and upper bounds of the function. So we want to have a starting point and an ending point. We can't have no bounds because there's no way to compute or calculate an infinite amount of area. So here it is, definite integral notation. Number one in this activity says to estimate the definite integral of f from 2 to 14 by counting squares. Well, first of all, let me do this. I'm going to actually color in the exact amount of area from 2 up to 14. I'll use this green color right here. And if I color this in, you can see all the different regions or this big section of area that we want to compute. So there it is. And of course, it's not really geometric. I have a curve on the upper part of it. So it's not easy to find exactly what that area is going to be. But if I count squares, I could get pretty close. Notice that one square unit here is, or one square is 20 square units. It's going to be very cumbersome to do that. So that's what we did at the beginning of the year when we talked about the concept of the definite integral. And by the way, look at the notation here. The integral from 2 to 14, I let my lower bound be 2, my upper bound be 14, and we're just going to put those bounds right there attached to the integral symbol. The function f is the integrand, and then dx is that differential that should be at the tail end of all of our integrals. Now, let's bypass square counting for now, since that can be very complicated, especially when the functions get larger and there's much more area to compute. Number 2 and number 3 kind of go together. Number 2 says to find an estimate of f of c for these varying values of c. And what I want you to notice is that these c values on the table are all in the middle between 2 and 4, and then between 4 and 6. They're actually midpoint values. F of 3, f of 5, f of 7. And so what I did is I actually put the function outputs there for you. You can jot them down. They're called sample points. And 3 would be kind of, again, in the middle over here. And then here's 5, 7, 9, 11, and 13 would be my last one. And if I find where those function outputs would be, if I just were to plot them, it would look something like this. I'm just putting little points on the graph to where those midpoint sample points would come up to. And then number 3 says to do this. On the figure, draw rectangles. And we're going to let the rectangles fill in the region under the curve and then help us more effectively find an approximation for the area. So ultimately here I'm going to have 6 rectangles in this diagram. And by the way, this delta x notation that we're going to see in a little bit, delta x represents the width, is the width of each rectangle. So in my diagram here, I'm going to let delta x be 2. So there's one delta x from 2 to 4. Another rectangle's width would fit between 4 and 6, and so forth, all the way across until I get to x equals 14. Delta x represents the width of the rectangle. Now, what about the height or the length of the rectangle? Again, that's going to be found by the sample points that we listed out. So in the first region, I'm going to construct a rectangle and make it go all the way up to my midpoint. And maybe it would look something like this. I'm going to draw it in. I'll actually put some texture to it here. And then the second rectangle, I'll draw that one. And again, I'll color it in for you so you can see kind of the difference. Here's the third rectangle. Notice that third rectangle and the first rectangle, it's not a perfect match. I'm sort of underestimating the function area at some point, and the corners are also coming up above the function area in another point. So it's not perfect. It's simply an estimation. But I want these rectangles to come all the way up to those sample points. I'll color them in. Here's rectangle 5 between 10 and 12. This looks like we're covering much more area now. These lengths or the heights of the rectangles are growing. And then finally, here's my tallest rectangle between 12 and 14. I'll bring it up to that sample point. And that'll be the last one. Again, feel free to color in those rectangles. If you want to shade them or use a highlighter, you can get creative with kind of how you color them, colored pencil, the outline maybe. And there we have it. So 6 total rectangles constructed on top of the region that I'm trying to find the area of. Now, together, collectively, if I add up all of the areas of those rectangles, I would get a pretty good approximation, not perfect, but an approximation for the area under the function curve. And that sum of the area of all those rectangles, of all those areas, we call a Riemann sum. So, specifically, this one is a midpoint Riemann sum. Midpoint because we used sample points that were at the exact center, the middle of my delta x values. If my delta x's were 2, then I would want to go halfway between my 2 to find, in this case, 3, and then 5, and then 7, and those sample points would be the midpoints of all of those intervals. So where do we go from here? Well, number 4 says to estimate the definite integral of f from 2 to 14 by taking the sum of the areas of all those rectangles. So essentially what we want to do is, from 2 to 14, this integral can be approximately equal to the first length times width of rectangle 1, plus the second length times width of rectangle 2, and plus the third, and so forth, all the way up to the final rectangle. But notice here in this problem that the delta x widths are the same. They're all equal to 2. So actually, what might be a little bit more efficient is if we factor out the 2 and then simply add up all 6 lengths or heights of the rectangles. But remember, the heights of those rectangles matched the sample point outputs. So my first rectangle had height of 17, the second one was 12, and then 15, and then 25, and then 38, followed by 45. If I compute that, I'll have an approximation of the area under the curve, which is the approximate value of the integral from 2 to 14 of f of x. Go ahead and compute that in your calculator. Don't forget proper units. It is an area calculation. So this integral is approximately 304 square units, or the integral value itself, if I remove it from the area context, we would just say equals 300, or is approximately equal to 304. Now, as we said, the sum of those areas was a midpoint Riemann sum. And we abbreviate that with this little M6 notation. So capital M for a midpoint, and then that subscript little number 6 just tells me how many intervals there are, how many rectangles I'm using to compute that sum. Now that's just one kind of Riemann sum. There are others, and I'd like to show you them next. So on the next page right here, I have another table of values, and we're going to use the same picture. But notice that the sample points have changed. Now I have f of 2, f of 4, f of 6, all the way down to f of 14. And I filled the table in with my approximations of what those sample points were. If you'd like to pause the video and take a moment to jot those down, this would be a good time to do so. Moving forward, number 7 says that these values, again, we call them sample points, but they will help us construct different kinds of Riemann sums. Okay, look down below at these two pictures. The same function is sketched, and we're still going from 2 to 14 as our lower bound and upper bound. But the rectangle heights, the rectangle sample points have changed. In my first diagram here, which is purple, all of these rectangles are actually rising up above the function curve. So every single one of those has an overestimation of area. And so the end result is that this Riemann sum is going to be an overestimate. It's going to be the sort of the maximum estimate that I can use. And so what I'm doing is I'm just picking the highest corner or the highest location of the function between 2 and 4, and then the highest point between 4 and 6, the highest point between 6 and 8, the highest point between 8 and 10. And I'm letting those rectangles rise up to that high point. And notice, look at where all the error is. All of the error happens to be above the function curve. So we have an overestimation in this case. So we call that an upper Riemann sum. Upper Riemann sum. In the blue picture over here on the right, I have an underestimation where now I'm choosing the lower of the two sample points. Between 2 and 4, what's the smallest height of the rectangle? Between 4 and 6, what's the smallest height of the rectangle, and so forth. And notice that all of the error is below the function curve. So all of these rectangles together, when the areas are added together, comes up with, or essentially make up, an underestimation of the exact value of the definite integral. We call this a lower. We call this a lower Riemann sum. So all of these Riemann sums are essentially just letting rectangles fill the region. And because rectangles are a pretty easy geometric shape to compute the area of, length times width is all we have to do, base times height, that's it. It becomes a pretty nice way to approximate the area under a function curve. And it's not perfect, they're all approximations, but we kind of get this idea of how rectangles can help to fill the region under a curve. So upper Riemann sum, lower Riemann sum, and we have two other kinds of Riemann sums, and those are left and right. Left and right. Sometimes we'll say left hand or right hand Riemann sum so that we don't confuse the L with the L for lower. By the way, abbreviations, again, it's U sub 6 for upper Riemann sum, capital L sub 6 for a lower Riemann sum. You can see those abbreviations here on the notes. And then 8 and 9 on this worksheet here are asking you to examine which function values would be used for a perfect left Riemann sum, a left-hand sum. Well, that just means we want to use the left corners all the way across. So my left Riemann sum would utilize the left corner, so f of 2, and then I would use f of 4, and then I would use f of 6, all the way up until f of 12. I don't want to use f of 14 as a sample point for this Riemann sum because f of 14 is a right corner of that far rectangle. Same question. Number 9, just flip the Riemann sum around. What about a right side or right-hand Riemann sum? Well, now let's just use the right corners. F of 4 would be my first sample point, followed by f of 6, and I would continue all the way out to f of 14. And I would use those. Of course, I would also need to have my delta x multiplied by that sum to create the Riemann sum approximation. And then number 10. All this discussion in theory is great. It's nice. It's a nice way to kind of think about definite integrals and approximating them, but there still is quite a bit of error. So what could we do to improve upon these approximations? How can we make, question 10, how can we make the definite integral estimate more accurate? And very simply this, use more rectangles. Increase the number of rectangles. Increase the number of rectangles in the Riemann sum. We use 6 rectangles in these pictures. What if we had 12 rectangles? Or what if we had 100 rectangles? What if we had 5,000 rectangles between 2 and 14, and we just stacked them together, closer and closer together, fitting them in perfectly between that 2 and 14 bound? Well, one thing, the widths would be really, really skinny, the more rectangles that I use. So we've got a limit happening here. The number of rectangles, we want to approach infinity. The more rectangles we use, the more intervals we use, then the more compact, the tighter together they're going to become, and the less error there will be. And that's the same thing as saying that we want delta x, the width of each of these rectangles, to essentially approach 0. We don't want it to be exactly 0, because then we have no area. There's got to be some dimension there so that I can compute a length times width area and then add up all the areas across the region. And then one last comment, it is possible that we might have delta x's or the widths of these rectangles not be uniform. In these examples here, all of the delta x widths were equal to 2. That won't always be the case. You might have a very thin rectangle and then maybe a wider rectangle. Delta x might be 1, delta x could be 5 or 7, and in this picture here in 11, I just drew a sample where you see some rectangles and they have varying delta x's. The widths are sometimes skinny in places and wider in others, and that's also possible for some of these Riemann sum approximations. So, to conclude, Riemann sums are a way to approximate the value of a definite integral. There's going to be some error. Could be an overestimation, could be an underestimation. We have 5 total Riemann sums. We have a midpoint, a left and a right, and then a lower and an upper. And you will have to read carefully to make sure you write down the appropriate kind of Riemann sum approximation that the question is asking you to compute or to approximate. And finally don't forget about the trapezoid rule. Not technically a Riemann sum because trapezoids aren't rectangles, but we also have looked at using trapezoids to kind of fit in between bounds and approximate function values as well. So 5 Riemann sums plus the trapezoid rule make 6 different methods altogether to approximate definite integrals. So I hope this tutorial was helpful for you. Feel free to pause the video and rewind, fast forward, and double check anything that you need to as far as details are concerned. And practice building some of these Riemann sums on your own. Make them be creative, make them colorful, and you can get a nice appreciation on how we can use these rectangles to create a nice visual image for what might be the area under the function curve as it presents itself. So good luck to you, and enjoy the rest of your studies on integrals.